It's a great pleasure for me, and I'm grateful for this opportunity to share my research. So today we're going to talk about alcohol, and let's start with a few numbers. Do you have an idea how much alcohol you drink per year? In this map, released by the World Health Organization, you can see the average alcohol consumption per country. And as you can see, in Belgium, people drink a lot of alcohol. And they drink exactly 12.6 liters of pure alcohol a year. What does it mean? It represents roughly 1,000 beers per person per year, or 90 bottles of vodka. Excessive alcohol consumption leads to issues which are found across the whole lifespan. So, drinking alcohol during pregnancy leads to defects which can range from mild mental retardation to very specific and facial abnormalities that you can see on this picture. And prenatal alcohol exposure is the first non-genetic cause of mental retardation. During childhood, an alcoholic family environment is a burden for too many children. During adolescence and adult life, binge drinking and alcohol addiction profoundly impact the life and health of many people. And finally, later in life, alcohol leads to organ damages and dangerous interactions with medication. So we have a project in the lab running on prenatal alcohol exposure and the development of the brain, but for sake of time I'm not going to talk about it today, and I will focus mainly on adolescent and adult alcohol consumption. So before going to the research per itself, I think it's important to regularly remind people how much alcohol impacts our body. Alcohol is responsible for the development of many cancers, liver cancer, esophagus, throat, pharynx, and so on. Alcohol is also toxic for the brain and leads to encephalopathies, but also defects in memory, and it can also lead to the development of psychiatric disorders such as, I don't know why this thing is moving like this, but just change this. Okay. So alcohol also affects the heart with cardiomyopathy, stroke, hypertension and so on, and the digestive tract is also impacted by alcohol. So we can talk about the famous liver cirrhosis, but also pancreatitis, chronic gastritis and so on. And this is a bit less known, but alcohol also acts on the muscle and neuropathic nerves, leading to chronic fatigue and neuropathies. And this is without taking into account accidents, violence, domestic violence, and so on. And altogether, alcohol is the fourth cause of mortality worldwide, and is responsible for 3.3 million deaths annually. So, now I hope you are scared enough to pay attention to the rest of my talk. When we talk about alcohol, we often think about alcoholism. So, alcohol addiction is a chronically relapsing disorder characterized by the loss of control over consumption. Alcoholics drink alcohol in spite of adverse consequences, and this is really important. That's how we define alcohol addiction in science, is the loss of control and drinking in spite of adverse consequences. In our country, 1 in 10 people has difficulties to control its consumption. And unfortunately, treatment options are very limited. 3 molecules currently exist on the market, and their efficiency is rather low, as less than 1/3 of the patients do not relapse within 10 years. So, in my lab, what we study is how do we become alcoholics? How is it possible that a small molecule such as alcohol can impact the brain to a point when people get drunk before 10 a.m. and basically kill themselves? That's the question we're trying to answer. So to understand alcohol addiction, it's important to look at our brain and what happened in our brain in front of an alcoholic drink. So to summarize, there are 2 main brain regions involved in the control of alcohol consumption. The first one is the striatum. It is a basic, primitive brain region. It is part of the reward system, and its goal is to seek for pleasure and drives habits. The striatum is somehow the bad guy, the little voice saying, drink. In opposition, we can see the prefrontal cortex, which is a much more evolved brain region. And it is really the master of control. It allows us to control emotion, impulsivity, and if we are able to make decisions, it's thanks to this brain region. So you've guessed right, the prefrontal cortex is the good guy saying, do not drink this one. So in most of the cases, prefrontal cortex controls the striatum, and that's why we are able to control our drinking. The third thing I was interested in is what is the action of alcohol on the striatum. And those studies have been realized at the University of California, San Francisco, and you can see this beautiful building where I had the opportunity to do these studies. It was in the lab of the Professor Dorit Ron, and her lab is specifically interested in unveiling the mechanism which promote the transition from social alcohol drinking, meaning occasional and recreational use of alcohol, toward the development of excessive alcohol drinking and alcohol use disorders. So our hypothesis was maybe alcohol could affect directly the striatum to promote this transition from social to excessive alcohol consumption. And specifically, we were interested in a complex of protein called mTORC1, and you'll see they always have funny names. Why mTORC1? Because it's known to be important to form memory. So, what's the relationship between memory and alcohol addiction? They are very close. It is thought that drugs of abuse, including alcohol, they are able to usurp the normal mechanism of memory formation. So, a drug, alcohol in this case, will wrongly associate memory of pleasure with the taking of the drug. So if mTORC1 is important for normal memory, maybe it is also involved in the maladaptive memory that we can see in alcohol addiction. So we studied this complex, and we used mice. And you can see that those mice have the choice between alcohol and water in their own cage. And basically they will drink alcohol for 8 weeks, and along the 8 weeks their consumption will increase. And at the end of the 8 weeks, they consume excessively alcohol. So we looked at the possible activation of mTORC1 after alcohol drinking in the striatum. And this is what is shown in this picture. So this is the striatum of a water-consuming mice. And this is the striatum of alcohol mice. And when biomagnification, you can see red dots, and basically each red dot represents activated mTORC1. And I think it's pretty clear here that alcohol activates mTORC1 in the striatum. So our hypothesis was right. Alcohol activates mTORC1 in the striatum. That's great. But what is this function? How is it impacting alcohol consumption? So we treated those mice with a specific inhibitor of mTORC1, which is called rapamycin. And when we treat the mice with this inhibitor, you can see that their consumption is decreased by more than 50%. So this means that alcohol consumption activates mTORC1, which promotes alcohol consumption. So that's great, once again, but what's missing here? What's the point? How does mTORC1 promote alcohol consumption? And to make a very, very long story short, we identified a new protein called prosapip1. Speaking of funny names, this is a good example. And we studied its function, and specifically during alcohol addiction. And in this picture, you can see a green fluorescent neuron of the striatum. And I think you all know that neurons make thousands of connections with other neurons. And those connections, called synapses, they happen at very specific places on the neurons. And that's what's shown here at higher magnification. all those little protrusions from the cell membrane are called spines, and they are the place where neurons communicate with each other. And basically, the more a spine is big, the more the connection is strong. So we look at those spines after alcohol consumption, and what you can see is that those spines are much bigger, meaning stronger connections between neurons of the striatum. Now, if we remove presapip-1, you can see that those spines, they are very, very, very small. And if we remove presapip-1 from neurons when mice drank alcohol, you can see that we go back basically to the normal levels. So what we showed here is that presapip-1 will increase the size of those spines and will increase the connections of neurons in the striatum. So how presapip-1, does presapip-1 regulate alcohol consumption then? To answer this question, we use a paradigm called self-administration. So in this movie, you will see a rat, simply because mice drink during the night and rat during the day, so much easier to record a rat. And so those real rodents are trained to press on the lever. I don't know why it's not working. Sorry. Okay. So you can see that this rat press on a lever and receive a drop of alcohol. So it's totally voluntary consumption. So what we did is ask ourselves, what happens if we remove presapip-1 from their brain? So that's what we did, and how did we do that? We use a specific viruses that we can infuse in the brain, which basically will kill all the presapip-1 in the striatum. And when we do this, you can see that mice without presapip-1, in light red, they press less on the lever to receive alcohol. So that's great. It means that presapip-1 is really involved in alcohol self-administration. But what happens if we do the opposite? If we put a lot of presapip-1 in the striatum? And that's what we did using another virus. We overexpress presapip-1 in the striatum. And you can see that those mice in blue, they kind of press like crazy to get alcohol. So that's what we showed. So to summarize, we showed that drinking alcohol activates mTORC1 in the striatum. And mTORC1 increases the levels of presapip-1, which will reinforce the connections between neurons. And those reinforcement of connection between neurons will increase their alcohol consumption. So now at the Run Lab, they are trying to design inhibitors of this presapip-1, and those inhibitors maybe one day could lead to the development of new drugs to fight alcohol addiction. So that was for the first part. So let's come back to our brain in front of a drink. And what we showed is that drinking alcohol reinforces the connections between neurons in the striatum and basically makes the striatum become stronger. So, fortunately, not everyone who drinks alcohol will become alcoholic. And this is simply because the prefrontal cortex is still able to control the striatum. However, in people suffering from alcoholism, we can see that the prefrontal cortex is weaker and is too weak to fight the striatum. And at that point, the striatum takes over the control, and drinking alcohol becomes a habit, then a necessity, and that's how alcohol addiction develops. What I'm working on now is trying to understand where does this weakness of the prefrontal cortex comes from. Why do some people have a weaker prefrontal cortex and are just more prone to transition from social drinking to excessive alcohol consumption? So, for decades, alcohol addiction has been considered as a condition that develops in adults. However, more and more data are suggesting that the roots of alcohol addiction start to grow earlier in life and precisely during adolescence. One example is this epidemiologic study performed on 80,000 people in the US, and it shows a clear relationship between the age of the first initiation to alcohol, whatever the quantity, 1 sip or 1 bottle, and the risk of developing an alcoholic dependence later in life. And what you can see is that drinking for the first time alcohol before 13 increases by 47% the chance of becoming alcoholic later in life. And this risk decreased to 38% at 15, 25 at 17, and it's only 9% when people drink alcohol after 21. So that's kind of frightening. However, alcohol is the most consumed addictive substance in adolescents, and it's believed that 40% of college students regularly consume alcohol. By regularly, I mean 1 or twice a week. But even more concerning that the quantities they drink is the pattern of drinking. And in the US, and in Europe should be approximately the same, it's believed that 1/3 of teenagers regularly experiment what we call binge-drinking episodes. So binge-drinking, it's basically drinking a lot of alcohol in a short time. And as you can see, binge-drinking is reached with 5 drinks in 2 hours for men and 4 drinks in 2 hours for women. And by drinks we mean 1 unit of alcohol, either a beer, a small glass of wine, or 2 centiliters of whiskey. Binge drinking is particularly dangerous because it leads to high blood alcohol concentration and toxicity for the brain. But can we say that binge drinking is more dangerous for adolescents than adults? The answer is yes, simply because the adolescent brain is not mature yet. So in this picture you can see the brain maturation. So red and green parts are immature, blue are mature region. And you can see that after birth the brain continues to maturate until 20-25 years old. And this maturation, it goes from the back of the brain toward the more frontal region. And in consequence, the prefrontal cortex, our good guy, it's the very last brain region to become mature. And its peak of maturation precisely occurs during adolescence. And when we think about it, this immaturity of the prefrontal cortex somehow explains the stereotypical teenage behavior with misreading of social cues, increased impulsivity, desire for risk-taking, and somehow we can say that if adolescents always make wrong decisions, it's not their fault, it's mostly the fault of their immature prefrontal cortex. So our research goal, knowing all this, what are we studying now? So, as I said, human studies show that consuming alcohol during adolescence increases the risk of developing alcohol addiction later in life. So, our hypothesis is that drinking alcohol during adolescence could interfere with the maturation of the prefrontal cortex, thereby leading to a weak prefrontal cortex at adult age, which makes people more prone to develop alcohol addiction. And to study this, we use a mouse model of adolescent binge drinking. So this model is called drinking in the dark because mice drink during the night. Those mice voluntarily consume alcohol. There is no forced ingestion, there is no restriction in food or water. And basically they have access to alcohol for 4 hours a day during their adolescence. Adolescence in mice starts at 29 days after birth, P29, and they become adult after P40. So those mice will have access to alcohol for 10 sessions, 4 hours a day. And this model has been designed to model a situation in humans when adolescents binge drink twice a week between 14 and 18 years old. On this graph you can see the alcohol consumption of our mice, and what you can see is that females in orange drink more than males in blue. And those mice drink about 6 to 8 grams per kilogram of mice per 4 hours, and that doesn't mean anything to anybody. But basically, those mice drink the same amount of a human drinking a half a bottle of vodka in 2 hours. So, our mice drink during adolescence, and we studied their behavior at 2 different time points, either short term, at the end of adolescence, or long term, in adulthood. And they have access to alcohol only during adolescence, not during adulthood at all. So this model, like adolescent drinking between 14 and 18 years old, tested at short term at 18, or tested at long term at 35. So what do we study? We studied a lot of behaviors, anxiety, depression, cognitive performances, flexibility, and addictions. And all those behaviors, they mostly depend on the function of the prefrontal cortex. So if we see a deficit in one of those behaviors, we could think that drinking alcohol during adolescence may interfere with prefrontal cortex maturation. So, how do we study anxiety in mice? We use this apparatus called elevated plus maze. So, it is a maze 1 meter above the ground, and you can see that there are 2 open arms and 2 closed arms. So, mice are curious animals, and they have a natural tendency to explore their environment. On the other hand, they are animals of prey, and they don't like to be exposed. So, basically, the more a mouse is anxious, the more it will spend time in the closed arm and the less in the open arms. Here on this movie, you can see a mouse. At least you can see the tail. Sorry, black on black is not always easy. So this is a mouse who only consumes water, and you can see that it basically explores the environment, the open arm, the closed arm. So we measure the time spent by the mouse in the open and in the closed arm. And when we tested this short term, after alcohol drinking, meaning at the end of adolescence, we did not see any difference between alcohol and water consuming mice. Just like drinking alcohol during adolescence has no effect on adolescent behavior. However, when we test this in adulthood, so this is an adult mice who drank alcohol during adolescence. And you can see that this mouse is much more anxious. He spends much more time in the closed arm and in the center. And I think we can clearly see that he would like to go explore, but cannot do it. So that's what's shown in this graph. You can see in red that adult mice who drank alcohol during adolescence, they spend much less time in open arms. And this is a sign of increased anxiety. The second test we tested is the depression. So, what is a depressed mouse? To look at that, we use a test called forced swimming test. So, mice are placed in a jar filled with warm water and for 4 minutes. And you can see that at first mice, they swim actively, so of course we never let them drown. And afterward they are dried, warmed up and put back in their cage. So this is an actively swimming mouse. And you can see that at some point it just starts moving and float, immobile. And this floating is a sign of behavioral despair. It's just like the sign that the mouse has given up. And the faster a mouse immobilizes and the longer it stays immobile, the more it is depressed. So we record the time spent actively swimming and floating. And once again, during adolescence, we do not see any difference between water and alcohol mice. When we did the same test long term, I mean in adult mice that drank water or alcohol during adolescence, you can see that alcohol mice in red, they spend much more time immobile compared to the control. And this suggests that consuming alcohol during adolescence may increase or may lead to depressive-like disorders. So then we assessed the cognitive performances. So we used what is called a novel object recognition test. And so this test is for 5 days. So on the 3 first days, the mice are placed in the testing cage just to habituate them at the environment, to remove any stressful sights and so on. On the 4th day, the mouse is placed with 2 copies of the same object, so 2 red circles. And 24 hours later, one of the 2 objects is replaced by a new one. So normally, mice are curious animals, so they want to explore the new object, and they should spend much more time exploring the new object compared to the familiar one. So that's what we can show here. So this is a water mouse, and you can appreciate the time it explores the novel and the familiar object. So it looks at the familiar, but it knows it, it recognizes it, so it's not interested and prefers to explore the novel object. So we record the time spent exploring both objects, and we calculate what's called a discrimination index, meaning the ability of discriminate between the novel and the familiar object. And at the end of adolescence, we do not see any difference between alcohol and water mice. In adulthood, so this is an adult mice who drank alcohol during adolescence. And so we did the same, and you can see that it explores both objects the same way, just like it's not able to recognize the object it saw the day before. And that's what's seen in this graph. You can see that mice who drank alcohol during adolescence, in red, they have a discrimination index much lower than water mice. And in fact, this discrimination index is almost 0. So it means that they spend the same amount of time exploring both objects, just like they don't recognize it. Next, we tested flexibility. So what is flexibility? Is the ability to adapt its behavior according to changes in the environment. So to do this, we use reversal learning with this maze. So it's a circular maze with 20 holes around. And basically we put a mouse in the center, and we use strong light and loud music, so this environment is very hostile for the mouse, and all mice really want to escape this. And what we have is a little black box, as you can see on the picture, and we can put the black box on one of the holes, and the mouse will basically search for this black box where it can hide and feel secure. So this is the behavior of those mice. You can see that it starts to check the holes naturally. And it will check all the holes until it finds the black box. Once they find the black box, they are put back in their home cage. So the first step is the learning process. So for 5 days, twice a day, mice will learn the position of the box. And once they all know pretty well this position, we can do what's called reversal learning. So basically, reversal learning is to move the box from this position to this position. And mice have to unlearn the previous position to learn the new one. So this is a mouse who drank only water, and you can see that it goes to the previous position as expected. It's so that there's no black box, so it will continue to explore the environment until it finds the new position of the box. So what we measure is the escape time, so the time a mouse spent trying to find the black box. And short term, at the end of adolescence, there's no difference between alcohol and water consuming mice. So this is an adult mouse who drank alcohol during adolescence. And you can see that as the water mice, it goes to the previous location. But instead of trying to explore the other holes, it goes back to the previous position, saying, I'm sure it is there, I want to see the box there. So it's kind of a perseverance process. And finally it goes back to exploring all the holes and will finally find the black box. So I will leave it to find the black box. Yay. So that's what's shown here. So in red are the mice who drank alcohol during adolescence, and you can see that they need almost twice as much time as the water mice to escape, so to find the black box. And this is the sign of lack of flexibility. So this reversal learning is performed for 5 days, twice a day. Okay? And we are at the end of the reversal learning, so at the end of the 5th day. And this is a control mouse. You can see that it doesn't bother to check the previous position, it goes directly to the new one. But a mouse who drank alcohol during adolescence, you can see that it keeps going back to the previous location before finding the new one. And what's really interesting here is that flexibility depends almost exclusively on the prefrontal cortex function. So this clear defect in flexibility indicates a defect in prefrontal cortex functioning in our mice who drank alcohol during adolescence. So the last test we performed was to measure alcohol addiction. So on this movie, once again, it's a rat, because mice drink in the dark. Where is it? So you can see that there are 2 holes in the cage. So this rat will be presented with alcohol 20% or water. And no need to see that this rat is quite alcoholic. And this rat will drink in 30 minutes the equivalent of a human drinking half a bottle of tequila. So you can see that I'm not lying when I say that they consume voluntarily alcohol. I'm not forced to ingest. So you could say, okay, that's good, drink alcohol, but maybe it's just because he tried this one first, and it's just by chance. So that's why on this movie we exchange the bottle. So it's definitely not interested by water. So we measure alcohol consumption. What's happening? Okay, it's okay. I don't know. It's only this slide. I don't know why. It's okay. So it doesn't want me to show the results on alcohol consumption in mice. So just trust me when I say it. When we measure alcohol consumption in adolescence, we do not see any difference. But when we measure alcohol consumption in adulthood, we see that mice who drank alcohol during adolescence, they drink much more alcohol compared to water. So when we summarize all the behavioral consequences of adolescent alcohol binge drinking, we can see that there is no huge defect, no obvious defect, short term, meaning that adolescents who drink alcohol during their adolescence, when they are tested at the end of adolescence, they look perfectly normal. at least in mice. But when we test those mice in adulthood, you can see that they exhibit increased anxiety levels, increased depression, decreased cognitive performances and flexibility, and increased alcohol consumption and addiction. So what this study shows, and this is quite frightening, is that adolescent alcohol binge drinking alters prefrontal cortex function, but silently, insidiously. And it leads to the silent development of behavioral deficits which are only observed in adulthood, when it's basically too late. So now for the rest of, for the follow-up of our studies, we are trying to unveil how does alcohol impact adolescent prefrontal cortex. So by using this kind of mouse model that I showed today, we are studying prefrontal cortex maturation. We are also looking at prefrontal cortex neurons, meaning their number, their survival, their morphology and the connection between neurons, and also the way neurons in the prefrontal cortex talk to each other and to other brain regions. And all of this to understand how alcohol binge drinking lead in adulthood to a weak prefrontal cortex and make people more prone to develop alcohol addiction. So I thank you for attention, and I'm here to answer any question you may have.